Okay. Okay. So yes, you'll have a homework assignment due this Friday. Any questions about anything? We're supposed to get bad weather this week, another hurricane. So maybe it's a good thing that we're doing it online. Well, except the power goes out, I guess, but that we can't control at all. Okay, so I'm going to share my screen. We'll get started this morning. Oops, wait a minute, I forgot to record. So go back. Okay, now. All righty. Okay, so let's see. Two people in the waiting room. All right, let's go back. If I do this too much, my internet kicks out. Okay, we've been talking about. I surely wish I could figure out how to get Mr. Miller to do this. All right, let me go back and let Mr. Stout in. It would also help if people would get there on time. Okay, differentiation rules. And we've been talking about this for, at least a week now. Here's a summary of what we've done so far. And I used some different notations kind of on purpose so you would get used to them. Remember that we have a function f. F prime is the notation for the derivative of f, and so is d of f, and so is df dx if f is a function of x. Okay. And you'll also see dy dx if f of x is equal to y. Okay, so the derivative of a constant is 0, constant regarded as a function. Power rule. Some of these have names. This one's generally called the power rule. The derivative of x to the n with respect to x is n x to the n minus 1. One thing kind of nice about this Leibniz notation, which is this notation and also this, it's sort of keeps right in front of you what your variable is. So X is your variable here. And then, okay, switch notation. If you have a constant times a function, the derivative of that function is the constant times the derivative of the function. That's number 4. If you have the sum of two functions, the derivative, no, that was number 3. Number 4, if you have the sum of two functions, the derivative of that sum is the sum of the derivatives. Okay, that's that one. Likewise, for the difference of two functions, if you have the product of two functions, f times g, the derivative of that whole thing is f prime times g plus f times g prime. This is generally called the product rule. Quotient of two functions. Derivative of quotient is f prime times g minus f g prime all over g squared. And we talked about the chain rule. Okay. That's a composition of two functions. That little circle means you take the composition. So g is essentially inside the function f. You have the composition of two functions, f and g. That derivative is the derivative of f composed with g. So that's another composition there, multiplied by g prime. Okay, we spent a couple of days talking about chain rule. Thought we'd spend today talking about the derivatives of the trig functions. I already told you that the derivative of the sine of x is cosine of x, but let's see why that's true. One fact we need to know is that this limit, the limit as x goes to 0 of sine of x over x is equal to 1. Now, proving that, well, I could give, there's a very nice little geometric argument you can give to actually prove that, but it would take me essentially a whole hour. So, and there's another tool called L'Hopital's rule that you're not going to learn about this semester. You'll learn about it next semester. It's a really powerful tool for evaluating some limits. That could be used to show this pretty quickly, but we don't know that yet. But let me just show you a graph. Okay, I took a picture off my other computer this morning. Where is it? My photos. Yeah, there it is. This is the graph of, I guess my pencil won't work on that. Okay. This is the graph of the function sine of x over x. I used a computer algebra system called Maple. Okay, and I told the machine to graph it between minus 0.1 and 0.1. And okay, so this graph, it ignores the fact that at 0, what you get is sine of 0 divided by 0, which is 0 divided by 0. So 0 is not in the domain of sine of x over x. But so even though there's actually a little thing missing there at 0, little hole. Oh, it did make a mark. Huh. Okay. Had to figure that out. It just goes right through 1, right? So this is sine of x over x. That provides strong numerical evidence that the limit is indeed 1. Let me go back to my notes. So we're just going to use this fact. And we're also going to need a trig identity, the sign of the sum of two angles alpha and beta is the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. Okay, so let's find the derivative of the sine function. And go back to the definition. Definitions are so important. When you encounter something new and none of the things you've learned so far tell you what to do, you go back to what the definition is. So by definition, the derivative of the sine of x is the limit as h goes to 0 of sine of x plus h minus sine of x over h. Okay, that's right here. And right here is where I use this identity. Okay, I put in x for alpha and h for beta in this next line. So sine of x plus h is replaced by sine x cosine h plus cosine x sine h. And then I still have my minus sine of x all over h. Okay, so let's see, that should go all the way over. So what am I going to do? Well, I'm gonna break this limit up into the difference of two limits using the limit laws. Okay, so I want to rearrange things. I'm gonna write the numerator in a different way. Okay, and then break it into two fractions. Not x, h. So sine of x cosine of h minus sine of x all over h plus right. I rearranged it. Okay, so I've got that. Now I have the sum of two things inside the limit, so I can break it into the sum of the limits. And then, okay, I can pull some things out of the limits. It's in the limit, it's h going to 0. H is changing, not x. Relative to these limits, x is a constant, okay? And that's going to allow me to pull some things out. All right. Let's do it inside first. I can factor the sine of x out of this first fraction. And there's a cosine of x multiplied there too. So not infinity, 0. Okay. Cosine of x times sine of h over h. And then the sine of x and the cosine of x can come out of the limits because they don't have any h's in them. Just using the limit laws here. Okay, so I've got that limit and that limit. And we just talked about the limit as x goes to 0, sine of x over x being equal to 1. So I can replace this with 1. And I've still got some work to do on this other side. Okay. I'm just going to leave it blank there. Let's work on this limit. The limit as h goes to 0 of the cosine of h minus 1 over h. Yes. I'm going to use this conjugate trick. Just using it on something besides a square root. Okay, so really multiplying by 1 there. Just change that minus to a plus. And what that does for me, cosine h minus 1 times cosine h plus 1 is cosine squared of h minus 1. Remember, the middle term goes out. That's kind of the whole point of doing this. Middle term's 0, that is, over h times cosine of h plus 1. Okay, and then another identity is that sine squared of h plus cosine squared of h is 1. And h can be any number, and it's still true. So cosine squared minus 1 is equal to minus the sine squared, and I cannot forget my limit. Oops. Okay, so that's minus the sine squared of h over h times the cosine of h plus 1. Okay, but this was kind of an aside. Let me come down. I'm going to break this into a product. Okay, I can break it into minus sine h over h. Well, the minus can just come out. I just take that, okay. And then I have another sine h over cosine h plus 1. Now, the limit laws say I can break that into the product of two limits. The limit laws behave nicely relative to products than the differentiation laws do. Okay, and there's that sine h over h thing, h going to 0. So this first one is 1. And then, okay, the second one, well, the second one's not 0 over 0 form. The limit as h goes to 0, the sine of h is 0. But cosine of 0 is 1. So that's 1 plus 1 in the denominator. Then we can just use direct substitution, 0 over 2. And 1 times 0 over 2 minus 1 times 0 over 2 is just 0. Okay, so all of this is to figure out that we have a 0 there. And there you have it. The end result is cosine of x. So we proved that the derivative of the sine is the cosine, but we did use something that we haven't proved, namely that the limit as x goes to 0, sine of x over x is equal to 1. Any questions? Okay, I'll take that as a no. Let's do the cosine. Okay, it's very similar. So now we know the derivative of the sine function is the cosine function. One thing I should mention too, in calculus, you want to take your angles, your x's here to be in radians and not degrees. Okay, radians match up with the calculus really well because they're a natural way of thinking about things. Degrees, well, a lot of, I guess, problems come in the form of degrees, but you really want to measure your angles in radians. Okay, so let's find the derivative of the cosine function. So using a definition, the derivative of the cosine is the limit as h goes to 0 of the cosine of x plus h minus the cosine of x over h. And I need another identity here, the one about the cosine of the sum of two angles. The cosine of alpha plus beta is, I didn't leave enough room. Hate to write it on 2 lines. Okay. The cosine of alpha plus beta is cosine of alpha, cosine of beta, minus sine alpha, sine beta. So we kind of need that identity. Okay, so the derivative of the cosine of x is this limit, and I'm going to use this identity next. So that's going to give me the limit as h goes to 0 of cosine x cosine h minus sine x sine h minus cosine x all over h. And I'm going to break it into the fraction inside that limit into the sum of two fractions, just like before. So let's see, I'm going to keep the cosine part together. And the sine of x part together. Oh, it's minus. So I just rewrote that fraction in the previous line as a difference of two fractions. And then my limit laws say I can write that as a difference of two limits. And then, okay, again, it's h that's going to 0. The limit, the h is changing, the x is not. Okay, so I can pull the cosine of x and the sine of x out. So we have then cosine, whoops. We have cosine of x times the limit as h goes to 0 of cosine of h minus 1 over h minus the sine of x times the limit as h goes to 0 of the sine of h over h. And okay, we are taking the limit as h goes to 0, sine of h over h be 1. And we just showed this limit is 0. Okay, so we wind up with cosine of x times 0 minus sine of x times 1. Sure, and that just gives you minus the sine of, whoops, nope. Minus the sine of x. So the derivative of the cosine of x is minus the sine of x. And the derivative of the sine of x is the cosine of x. And we've almost proven this. We just had to accept one thing, that the limit is x goes to 0, sine of x over x is equal to 1. Does anybody have any questions at this point?
No, ma'am.
Okay. Well, once we have these two trig functions, have the derivatives of these two, the others are easy, okay? Because now we can plug into some of our, well, what we already know about quotients and so forth. The derivative of the tangent of x, well, the tangent is the sine over the cosine. Oh yeah, I might mention, I expect you to be, well, to know trigonometry, basic trigonometry, okay, what these functions look like, the domains and ranges, and maybe I'll go over that after I get these things, these formulas derived. Okay, so the derivative of the tangent, well, tangent sine over cosine, so then I can use the quotient rule. So it's the derivative of the top function times the bottom function minus the top function, kind of like to put in parentheses to be absolutely clear, times the derivative of the bottom function, all over the bottom function squared. And the derivative of the sine is the cosine. And then sine of x times the derivative of cosine of x. Well, the derivative of cosine of x is minus the sine. And that's over the cosine squared. So that gives us cosine squared of x, and then minus times minus. That's sine squared of x. I only need a plus in the middle. Okay. Over the cosine squared of x. And what's cosine squared of x plus sine squared of x equal to? 1. Another identity. So the derivative of the tangent function is 1 over the cosine squared, but 1 over the cosine is the secant, so you can also write it as the secant squared of x. Okay, and then the cotangent Cotangent is cosine x. Having trouble making S's this morning. Cosine x over sine x. So that would be, again, that's a quotient of two functions. So it's a derivative quotient rule. Derivative of cosine x times the sine of x minus the cosine of x times the derivative of the sine of x over the sine squared of x. Derivative of cosine is minus the sine. And that's multiplied by the sine. Then you have minus the cosine. And the derivative of the sine is plus the cosine all over the sine squared. And that's minus sine squared of x minus cosine squared of x all over sine squared of x. I can pull that minus out of the top. And sine squared plus cosine squared is 1. So what I have is minus 1 over the sine squared of x. And 1 over the sine is the cosecant. So it's minus the cosecant squared of x. Okay. So that gets us the derivative of the tangent and the cotangent. And the secant and the cosecant are as easy. The derivative of the secant function, well, the secant is 1 over the cosine. And, well, I could use the quotient rule, or I could also just think 1 over the cosine is the same as the cosine of x raised to the minus 1. And then I have, okay, if I write it this way, I really have a composite function. Where the inside, I will do it both ways. I will do it with a quotient rule too. Inside function is the cosine of x, and the outside, which we'll call u, is u to the minus 1. So, oops, I need to put that d there. Otherwise, it's not true. So the derivative of the cosine of x all raised to the minus 1 is the derivative of u to the minus 1 times the derivative of the cosine. I've got u and x. Okay. The derivative of u to the minus 1, they use power rule for that. Oh, stop that. Okay, so that would be minus u to the minus 2. Yeah, remember the derivative of x to the n is n, x to the n minus 1, and n here would be minus 1. The derivative of the cosine function is minus the sine function. And then going back to my x's, u is the cosine of x. And then times minus the sine of x. So we've got minus minus. And what we've really got there is the sine of x over the cosine squared of x, which I can write as sine of x over the cosine of x times 1 over the cosine of x. is the tangent of x times the secant of x. So the derivative of the secant is secant x, well, okay, secant x tangent x. I just wrote it in different order. Let me show you that that also works using the quotient rule. Okay, I could have also used the quotient rule on this. So this is using the chain rule. We'll do it using the quotient rule. So my numerator is the function, constant function 1, and my denominator function is the cosine function. And the quotient rule then says that okay, I'll put in the x's. Sometimes you don't write them like I did when I put in the rules there. It's called suppressing the x. It's still there, you just don't see it. Okay, so the derivative of a quotient is f prime times g minus f times g prime over g of x all squared. Well, f prime is 0. F of x is 1. The numerator is 1. So that's 0 times cosine of x minus f of x, which is 1, times the derivative of the cosine, which we just saw is minus the sine, over the bottom function squared. Okay, so that's cosine squared of x on the bottom. And that's equal to what we got before, sine x over cosine squared of x, which is the derivative of the secant, but you could also write it as sine of x over the cosine of x times 1 over the cosine of x, which is tangent of x times secant of x. So we got the same thing either way. So we have now the derivative of the secant, and the cosecant's very similar. In fact, maybe I'll leave the details of that to you. The derivative of the cosecant is minus the cosecant of x cotangent of x. Okay. And again, you write it as 1 over the sine and go from there, either using the chain rule and the power rule combined, or just the quotient rule will also work. Okay, so let's make a list of all of these. Table. Sorry. The derivative of the sine of x is the cosine of x. The derivative of the cosine of x is minus the sine of x. You're going to want to remember these. The derivative of the tangent of x is the secant squared of x. The derivative of the cotangent of x is minus the cosecant squared of x. The derivative of the secant of x first. Okay, secant of x is secant x tangent x, and the derivative of the cosecant of x is minus cosecant x cotangent x. So now we know the derivatives of all the trig functions. Let's see, how much time do I have left? About 14 minutes. Let me say, okay, we're going to do lots of problems now with these functions involved, but maybe I'll save that for tomorrow. Let me just go through a quick review of these trig functions. Okay, the sine function has domain all the reals, and range -1 to 1. And it looks like periodic. All the trig functions are periodic. Okay, so that's 1 and -1. Okay, keeps going on this side. Yeah, should be further over there. But let's see. Pi is where it's equal. Multiples of pi are where its sign goes through 0. Odd multiples of pi over 2 are where it takes on the values +1 and -1. Okay. You should have images of these in your mind. The cosine is actually just the sign shifted over by pi over 2. Just take it and move it that way. Cosine has domain R, all the reals, and range also -1 to 1. Cosine of 0 is 1. And then it comes through 0 at pi over 2. And -1 at pi, back through 0 at 3 pi over 2. And keeps going and keeps going. Okay. That's a sine graph, cosine graph. And those are the only two whose domain is all the reals. The tangent function, okay, you're dividing by is sine over cosine. So you're dividing by the cosine function. Any place that the cosine is 0, you have a vertical asymptote for the tangent. And of course, it's not defined there. The domain of the tangent, well, it's a union of a lot of intervals. 1 around 0 is -pi/2 to pi/2. Yeah, cosine is 0 at pi/2, and that means the tangent's not defined there. Cosine is 0, cosine of -pi/2 is 0, so tangent's not defined there. So you got, in fact, vertical asymptotes at all the odd multiples of pi/2. There's a ... and then it goes on in the other direction too. -3 pi/2 to -pi/2. Keep going. So, okay, and the range of the tangent is all the reals. And the domain and the graph, okay. 0, call that pi over 2. Call that 3 pi over 2. Call that minus pi over 2. A vertical asymptote at these odd multiples of pi over 2. And in between, goes like that. Like that. That would be 0. That would be a pi. And of course, it keeps going. And it keeps going. Okay. That's what the tangent looks like. And then the cotangent, okay, well, that's cosine over sine. So anywhere the sine is 0, you have a vertical asymptote for the cotangent. So its domain, oops, don't write that. That means derivative. That would be a union of a lot of intervals too, okay? But 0 to pi, these are going to have endpoints, the integer multiples of pi. Back the other direction. And its range is also all the reals. So, and its graph, well, the y-axis is actually a vertical asymptote for the cotangent. So, right over it, okay. All integer multiples of pi are asymptotes. Okay, and then, well, it's one of the tangents, so it's going to come in like this. That's a lot smoother than I'm making it. Okay, very rough. The graph looks like that. The secant, okay, that's 1 over the cosine. So it's going to have a lot of vertical asymptotes. And anywhere that the cosine is 0, which means at odd multiples of pi over 2. So let's see, its domain, well, same as the domain of the tangent. Minus 3 pi over 2. Minus pi over 2. Okay. And range, okay, well, it's 1 over the cosine. So it can't possibly take values in between -1 and 1. Its range is minus infinity up to -1, union 1 to infinity. And the graph, okay. That's 1. And then on the here, okay, -1 would be the highest point. Comes down. Over here, it's one of those. And in the next one, one of those. So it looks like that. Okay, periodic. Vertical asymptotes. And the cosecant is just that shifted over. Okay, so the cosecant, let's stick with black. That's 1 over the sine. All right, so its domain, same as the cotangent, 0 to pi. Union pi to 2 pi, union dot dot dot, a union minus pi to 0, union dot dot dot. And the range is the same as the secants for the same reason. You take them 1 over the sine. Everything up to 1 union 1 and up. And okay, so it's 1 over the sine. So that means that the y-axis is an asymptote. And at pi over 2. And then 2 pi, 1 minus 1. And then, of course, it just keeps going, repeating that. One of those over there, and one of those over there, and so forth. That's the cosecant graph. Okay, so yeah, that gives you domains, ranges, and some rough pictures of what those graphs look like. You should have those graphs kind of in your mind, graphs of the important functions. I also expect you to know your special angles, which are, and the trig functions at your special angles. Okay. 0, pi over 6, pi over 4, pi over 3, and pi over 2. And then, well, of course, once you know those, you know what the trig functions of 2 pi over 3 and so forth are using your unit circle. But yeah, you need to know those by heart. And not have to put it in a calculator. Now, if I ask you for the sine of 1, okay, well, that's not, 1's not a special angle. It's a number, but if I really wanted a numerical calculation of that, I probably would have to put it in a calculator, and I have to make sure that my calculator gave me the sine of 1 radian and not the sine of 1 degree too. Okay. Oh, I am out of time. Okay. Any questions? You can go, first of all. It's time for class to be over. If you have questions, hang around.
Have a good day.
You too.
Bye. Have a good day, Miss.